Welcome to Future Epoch, where we learn more about our world. For decades, it has been the punchline of physics. The joke goes that fusion power is always 30 years away, and it always will be. But something changed. In December 2022, a team of scientists at a laboratory in California produced more energy from a fusion reaction than they put in. For the first time in history, ignition had been achieved. And across the world, in the south of France, the largest and most complex scientific machine ever built was inching toward completion. The race to bottle the power of the sun was no longer a distant dream. The question now is whether we can cross the finish line before the problems that require fusion energy make that energy too late to matter. Fusion is the process that powers every star in the universe. Deep inside the sun, hydrogen nuclei are forced together under immense pressure and temperature, fusing into helium and releasing enormous amounts of energy in the process. The appeal of replicating this on Earth is almost impossible to overstate. The primary fuels, deuterium and tritium, are isotopes of hydrogen. Deuterium is extracted from ordinary seawater. Tritium can be produced from lithium. Neither is a fossil fuel. Neither produces carbon dioxide, and the reaction itself creates no long-lived radioactive waste. The potential output is staggering. A single kilogram of fusion fuel contains the energy equivalent of roughly 10 million kilograms of coal. The problem is that making fusion work requires extraordinary conditions. To force nuclei together, you need to heat a plasma to approximately 150 million degrees Celsius, 10 times hotter than the core of the sun itself. At those temperatures, no physical material can contain the reaction. No metal, no ceramic, nothing solid can touch a plasma that hot. Instead, researchers use powerful magnetic fields to suspend the plasma inside a device called a tokamak, a torus-shaped chamber where the plasma floats, held by invisible forces, while the fusion reaction proceeds within it. The idea of harnessing fusion energy is nearly as old as nuclear physics itself. In the 1950s, researchers in the United States and the Soviet Union began developing experimental reactors almost simultaneously, though much of this early work was classified. By the 1960s and 1970s, the tokamak design, pioneered by Soviet physicists, had emerged as the dominant approach. Progress was steady but slow. Each generation of machine produced more plasma energy than the last, while consistently demonstrating just how much further there was to go. The defining project of modern fusion science was born from an idea proposed at a summit between Ronald Reagan and Mikhail Gorbachev in 1985. ITER, the International Thermonuclear Experimental Reactor, would be the machine to prove that fusion could produce net energy at scale. 35 nations eventually joined the collaboration, making ITER the largest international scientific cooperation in history. Construction began at Cadarache in southern France in 2010. When complete, ITER will stand nearly 30 meters tall, weigh approximately 23,000 tons, and generate 500 megawatts of fusion power from just 50 megawatts of input, a tenfold return on investment. Alongside ITER, other machines were pushing the boundaries of what was achievable. The Joint European Torus, known as JET, operated at Culham in the United Kingdom for over 40 years and served as the principal testbed for the plasma physics that ITER depends upon. In February 2002, JET set a world record, sustaining a fusion reaction that produced 59 megajoules of energy over 5 seconds, more than doubling its own previous record. It was the final major experiment JET conducted before the machine was decommissioned. The baton had been passed. Then came December 2022 and the National Ignition Facility in California. Using an entirely different approach known as inertial confinement, in which 192 powerful lasers were directed at a pellet of fusion fuel no larger than a peppercorn, researchers achieved ignition. The reaction produced more energy than the lasers delivered to the target. It was a scientific milestone decades in the making. Yet for all of these advances, the fundamental challenge of fusion remains unchanged. The gap between a scientific demonstration and a working power plant is enormous. ITER itself is not a power plant. It is an experiment. When ITER eventually achieves its design performance, it will not generate a single watt of electricity for the grid. Its purpose is to demonstrate the physics and the engineering that a future power plant would require. That next machine, known as DEMO, remains largely a concept. If ITER succeeds on schedule, a commercial fusion power plant might not exist until the 2060s or later. ITER has also been battered by delays and cost overruns. The project's total costs are now estimated at over €20 billion and rising. Timelines have repeatedly slipped. First plasma, originally projected for the early 2020s, has been pushed back multiple times and is now targeted for the mid-2030s. Components manufactured in different countries to tolerances of fractions of a millimeter must fit together perfectly inside a single machine, and when they do not, years of work must be revisited. The engineering constraints go beyond scheduling. Tritium, one of the two primary fuels, is extraordinarily rare on Earth, with the global stockpile measured in kilograms. A commercial fusion power plant would need to breed its own tritium from lithium blankets surrounding the reactor core, a process that has never been demonstrated at the scale required. Materials exposed to sustained neutron bombardment inside a fusion reactor degrade in ways that remain poorly understood at operational timescales. These are not unsolved problems in principle, but they remain unsolved problems in practice. Into the gap between experiment and power station, a wave of private investment has arrived. Companies including Commonwealth Fusion Systems, Helion Energy, TAE Technologies and General Fusion have collectively raised billions of dollars in the belief that private ambition can compress timelines that government programs have been unable to meet. Commonwealth Fusion Systems, the spin-out from MIT, is building a compact tokamak called Spark that uses high-temperature superconducting magnets to achieve magnetic fields far stronger than those in ITER, potentially allowing a much smaller and faster device to reach the conditions needed for net energy gain. Helion Energy has signed a power purchase agreement with Microsoft, promising to deliver fusion electricity by 2028, a date that most physicists regard as extremely ambitious. The scale of what fusion could deliver, if it works, is difficult to overstate. A successful fusion power program would offer effectively limitless low-carbon energy, with no greenhouse gas emissions, no risk of nuclear meltdown, minimal long-lived radioactive waste, and fuel sources accessible to virtually every nation on Earth. In a world already suffering the consequences of carbon-intensive energy systems and facing continued growth in global electricity demand, fusion represents something rare, a technology that could genuinely alter the trajectory of civilization. The risks of failure are equally significant, though less dramatic. If fusion power arrives in the 2060s or later, it will be too late to contribute meaningfully to the energy transition that the next 30 years demand. The climate problem is not waiting for experimental physics to conclude. Fusion's promise has always coexisted with the danger that by the time it is ready, the need will have been met by other means, or the consequences of failing to meet it will already have accumulated beyond remedy. What the history of fusion teaches is not that the technology has failed. The physics is sound. Every decade of research has produced more capable machines and a deeper understanding of plasma behavior. What fusion teaches instead is that the distance between a valid scientific idea and a deployed technology is measured not only in years but in engineering challenges that only reveal themselves when you begin building at full scale. The shift now underway, with governments committed to ITER and private companies pursuing faster parallel paths, is the most serious attempt ever made to close that distance. Whether any of the current projects will succeed on the timescales their proponents claim remains genuinely uncertain. What is no longer uncertain is the seriousness of the attempt. Humanity has spent 70 years learning to contain a plasma. The Sun has been doing it for 5 billion. The gap between those two facts is not embarrassing. It is simply an honest measure of the complexity of what is being attempted. But the machines are getting better. the magnets are getting stronger, and the investment is real in a way it has never quite been before. The question fusion has always posed is not whether the physics allows it. The question is whether human institutions, with all their funding cycles, political pressures, competing priorities, and shrinking timelines, can build the machine fast enough to matter. That question does not yet have an answer. But for the first time in the history of this field, answering it feels genuinely possible. Thank you for watching. If you've enjoyed this content and want to see more, please consider liking the video and subscribing to the channel.